So when I
The broadcast is now starting. All attendees are in listen-only mode.
Can you hear me now?
Yes.
Okay, great. So, let me start. Hello, everyone. Welcome to the week 3 for S2S webinar series. As many of you are aware, this monthly series is co-sponsored by the OAR Weather Program Office S2S program and the National Weather Service OSTI modeling program. So before forgetting, our next meeting will not occur in December and January. We will revisit our monthly webinar in February 2024. So my name is DK Kang. I'm from WPO S2S program. Before we begin, I wanted to remind everyone of the webinar series website. I'll post the website address in the chat box. There you can find information on the upcoming talk. Also, you can add yourself to the mailing list to stay informed. And also you can have an access to recording of the past talk. There is also a form available if you are interested in presentation of future webinar. So we currently have spot available over the next few months in the year of 2024, but we highly encourage you to consider giving a presentation. Lastly, if you have any questions for the speakers during the presentation, please post them in the discussion document, which I will share in the chat box. So today we have two speakers. The first one is Dr. Buhar Singh. Will update on the calibrated probabilistic subseasonal rainfall forecasting of the 2022 Pakistan rainfall. After that, our second talk will be provided by Dr. Joe Wang about a polar low genesis potential index and its application to subseasonal prediction. So with that, we will go ahead and get started, and I will turn it over to Buhar.
Okay. Can you hear me? Hello?
Yes, I can hear you.
Okay. So thank you for the introduction. Today I'm sharing our work with my colleague Mohammad Azhar Ehsan and Dr. Andrew Robertson. It is about Pakistan monsoon and its verification of our subseasonal forecast system for the year 2022. Monsoon of 2022 over Pakistan was had some interesting features, so that prompted us to investigate subseason. Pakistan is located at the northwest corner of South Asia monsoon region, and monsoon barely reach over Pakistan till July, and mainly it's remain our northern side, and the southern states like Balochistan and Sindh barely get a rainfall around less than 30 mm per season, per month. And monsoon take early recession from in September, then when it's going backward. So mainly rainfall happen only 2 months. And this is the seasonal forecast which is issued by SASCOF during 2022 with April initial condition, which was indicating above normal rainfall over Pakistan, and with quite a high, like a 45 to 55% probability over some regions. And but this is what actually happened over Pakistan. So in figure A, where my cursor right now, as you can see that more rainfall over Pakistan this season was forecasted above normal, and we can see that rainfall all over Pakistan is above normal, but in the south, which is very unusual, this region gets rainfall like around less than 100 mm per season, but this particular year it was well way above the annual mean. Like you can see that this is these two boxes. First is for northern Pakistan, and second one is for the southern Pakistan. And for the northern Pakistan, it's look normal. They're a little bit high above during June, July, and August month. But look at the southern Pakistan region. It's like a 4 to 6 time rainfall on those months. And when we look into the weeks when this rainfall happened, because we are interested on subseasonal time scale, you can notice that there are more than 30 mm rainfall happened during entire July. This is the aerial average. And then there is a 1 week break, and then 3 week of another spell. Those 2 spell of heavy rainfall impacted Pakistan adversely. They affected 33 million people, accounted for 1,700 deaths, and 15 billion of loss to infrastructural property, and also the around 7 to 8 million livestock losses their lives. So that was a devastating for the southern Pakistan, which is basically not prepared this kind of rainfall, because that never happened there. So aim of this study to look into the state of the art climate forecast system, how advanced they can offer some actionable information to this region to manage such climate risk. So we have used the ECMWF data from S2S, and which is a CY47R3 model, which gives us 46 day lead time, and for first 15-day model run at 16 kilometer, and after that 32 kilometer. And this model generate the forecast on the fly, a reforecast on the fly. So for the hindcast, we have used 2002 to 2021, and we have used the method of CPT of IRI. We have a Python wrapper for this we call PyCPT, and we have utilized the CCA method to calibrate those forecasts. ECMWF hindcast have 11 member ensemble mean. Of those 11 member is passed through CCA algorithm, and forecast have 51 ensemble member. Of the observed data, we have used SHERP, and then it has a module for skill assessment and forecast generation. Forecast is generated on deterministic, probabilistic, and flexible forecast format, in which we have information of whole PDF rather than those 3 categories. Skill metrics, we have used rank probability, skill score, and reliability diagram. And other detail that ensemble mean forecast are summed between for week 1, week 2, and week 3, 4. And we have verified forecast only for 4 initial conditions, though models initialized 2 times in a week. So there will be like 8 initial condition per month, but we have only focused on start date of early month to match their monthly forecast. And NOAA OLR data also used to understand how northward propagation happened during the season. And to train the model, we pooled 3 months centered around the forecast date, and that gives us 540 samples to train CCA-based regression model, and that enable us to use a retroactive cross-validation, and because we have enough sample. And forecast probabilities are obtained by the error variance around the mean. And this is the subseasonal hindcast skill. We can see that so those running 3-month season, May to July, June to August, July to September, and August to October, and the RPSS for the week 1, 2, 3, 4 remain positive, and those numbers are multiplied by 100. So generally, it's around 0.04, or less than that. And there is a small region of Balochistan where rain never happened. Rarely happen is a dry, and so it's giving us a negative RPSS. And I will want to clarify that we have used the total rainfall over 3 months. At the longer lead, some of skill may be because of climatology is not seasonal climatology is not removed. And we also did this experiment with anomaly by removing the seasonal cycle. The scale of first 2 week remains same, but for third week there are some skill from those models able to capture those seasonal cycle. So this is the reliability diagram in which we have all tercile 3 categories are pooled and all forecast over Pakistan pooled, and then you can see that forecasts are remain within the positive Brier skill scores. This means that those are reliable, and but they are sharp also for wide range of probabilities. But the higher probabilities models are our forecast are a little bit overconfident, and during their peak season of June to September, the forecasts are reliable and sharp. And this is the weekly and week 3-4 accumulated total rainfall. If we can see that the monsoon season over Pakistan start around last week of June, and then there is a July. There's a lot of rainfall continuously happening over southern part of the country, and and during then the break of 1 week and then another start, and by week of 12 to 25 August, there's a lot of rainfall. So and the September when monsoon is going back toward the Indian side, and there is no rainfall except some regions in the north and a little bit in south. This is the raw forecast of the model. Like if we do not do anything to the model forecast, we can see that model is able to capture those start of the season and continuous rainfall during July, even week 3-4 lead times, and in both July and August. So you can see that raw model forecast are doing pretty remarkable job in capturing those rainfall intensities with the magnitude and the spatial scales. Though you can see that there are some false alarm on those regions that the rainfall has never happened. Maybe those are spatial bias. So when those bias correction methods are applied to this raw forecast, we can get this downscaled forecast and bias corrected. But some of this bias still remain there. But you can see that our forecast has a as similar magnitude as observed, and this model is pretty good for the region. And this is the probabilistic forecast verification for those all 4 months. This is a June, July, August, and September. And this is a observed percentile between 1981 to 2022 for CHIRP data for 43 years, which every week is ranked every 3 to 9 June for every year. And if we can see that rainfall was in 100th percentile in July in the southern Pakistan. So these things over Pakistan never happened. And there is a large region during 12 to 25 of August have another 100 percentile pulse. So these 2 months was a nightmare for that region, a lot of rainfall, and the normal start around last week of June. And this is the probabilistic forecast from the model. So this is calibrated, and you can see that normal start of the season model is picking up. There's in week 1, which is possible. In week 2, models overconfident all over the Pakistan. It is very high probability, around 70 to 75%, but some of the region, specifically in the south, get a lot of rainfall, but most of the region is above 70 percentile. So those are above normal rainfall, except some regions. And week 3-4 of the July, you can see that this is the Sindh, this is Balochistan, and those regions get a heavy rainfall, and then that forecast is correct in the lead of week 3 and 4. However, in the August, you can see the large region is forecasted in right category, except in the southern and part of north. But the rainfall of heavy rainfall pulse of August is correctly predicted over the larger region. And then in the September model is also able to capture those like a region of above normal probability on the northern Punjab side, and thus over the Sindh. So overall model categorical probabilistic forecast is in a right category most of the time, except a few regions specifically in the north. And these information is useful up to 4 weeks. So this is tells us the information about categories in the above normal and how much above normal. We can also get the information from the flexible forecast format, because we have spread and mean. So we have a full PDF. So if we can ask the question, what is the probability of rainfall exceed some certain threshold or certain percentile? We are not in this, we are interested into threshold based rainfall, like a 30 mm per week and 60 mm if it is in week 3+4. Because in those regions of southern Pakistan is dry, and the PDF is very sharp. So every region will be above that 80% is if a little bit rainfall happen. So if we use 30 mm and 60 mm rainfall as a threshold, then the flexible forecast for models look like this. So this is the region where some areas has a rainfall more than 60 mm, then model is able to capture them over the large regions. And in week 1, model able to capture our Sindh and the southern Balochistan, and in week 2 also, and the northern Pakistan region, and in week 3-4 it is some kind of mess here, but some regions have a probability of having rainfall more than 60 mm, around 60%. And you can also notice that these regions which they barely happen, like a 30 mm rainfall models is also showing this probability of around 60%, and this happened because of those dry regions. It should be masked. And in week 3-4, when there is no rainfall in the south, rainfall move to the northern side, the probability of heavy rainfall is also going toward north, and then returning back north and south dipole models is able to capture that one also. And for the August rainfall, 12 to 25 August rainfall model is also captured this heavy rainfall over Sindh, but there is a false alarm over northern Pakistan. So, and overall models really good up to 2 weeks in telling us how heavy rainfall is coming to anticipate those flood-related risks. But week 3-4, it's marginal. So why this model's raw forecast is showing capturing those rainfall up to 3 to 4 weeks. To understand this, we look into monsoon interseasonal oscillation during 2022. This Muller diagram is the OLR, observed OLR, which is bandpass filtered for 30 to 90 days. And those contours are Lenchkos bandpass filter, which is, and this blue colors is raw anomalies for negative. Contours are only for the negative OLR anomalies to see this northward propagation. And as we can see that there are 3 distinct events happened during 2022, and on the right on the right side, I have concatenated all those monthly forecasts, which is started 2nd June, 29th, or 30th June, and maybe the 30th July, and 1st September. So we can see that models is also able to capture all those three northward propagation successfully. So this may be the region this model have a successful prediction of 2022 heavy rainfall events over Pakistan up to 2-week advance and give some guidance of a heavy rainfall probability, like above normal rain probability up to 4-week in advance. And a model is also able to capture this initiation in advance, like 20 days, but the model capture meso correctly if the mods are initialized when meso is already present into the initializations. So you can see these events are successfully captured. So this is if you look into detail, like this is average of our very large band 60 to 100. So we cannot say that when rainfall happened the meso was there, because this is not usual that meso goes toward Pakistan. These are going toward India after crossing the Bay of Bengal. They're rarely going there. So this is the looking at the 5-day average of OLR anomalies. And similar, this negative contours tell us there's a convective clouds. You can see that there is no organized structure in June, but in the June, at the end of the June, there was one event started, and it's remained stronger over the Pakistan over those all weeks, like all of July, and this coincide with the heavy rainfall event over Pakistan. The second event, which is started like around end of July, like 20th of July, it is also propagated northward, and this Arabian Sea branch remains stronger, while the Bay of Bengal branch become weaker, and it has stayed over Pakistan again, and that caused a heavy rainfall events between last 2 weeks of July. August, and there is another event started in 3rd week of August, and you can see that this event propagated northward, but it's not reached to the Pakistan latitude, and then we observed that there is a quite September over Pakistan. Only these 2 months and heavy rainfall coincided with these two events in observation, and you can see that model is also able to capture July event and August event, stronger Arabian Sea branch, weak Bay of Bengal branch. So the propagation of this September event away from Pakistan latitude. So the processes in the ECMWF models at subseasonal time scale represented rightly, and that gives some the predictability of week lead of week 3 to 4 times scale. So that's it. This system is useful. I have a information advance up to 4 weeks, and if it would have placed for Pakistan, this kind of climate risk should be anticipated, and some loss should be limited by using those subseasonal forecasts. That's it. Thank you for listening.
Thank you, Bohar. Yeah, there is a question in discussion sheet. Any from Nachiketa at S2S. Any reason why CCA-based calibration doesn't remove the false alarm from ECMWF?
Yeah, good question, Nachi. This one, okay. So what we did, like when we trained the CCA, our predicted and predictant domain, we keep same. And there is a possibility if we increase the domain at longer lead, like a predicted domain, I'll keep a little bit larger, then it is possible that CCA modes will able to capture that larger scale of meso and maybe that is the region, but we didn't explode in that direction. But this is just like a hypothesis.
Great. So if you can just fill out the answer at the end, it would be great. And then I have a quick question. Is there any elevation dependencies of the precipitation forecast? For example, from the Hindu Kush mountain to the sea, there is an elevation gradient, and any like forecast error variation, it will be found during your research.
And in this particular exercise, no, because we just took the forecast and just corrected, and we have not did any additional analysis on how the rainfall happened over terrain and on those plain regions.
Okay. Yeah, thank you. And I think any other questions from the audience? Okay, yeah, it would be much appreciated, Bohar, you can fill out the answers in the discussion document. And then let's move to the Jewel Wang. I will make you the presenter. Okay. Yep, I can see your screen.
Okay. Can you hear me okay?
Yep, I can hear you.
Okay, great. Thank you. Okay, I will talk about the polar low genesis potential index and its application to sub-seasonal prediction. Most of the analysis I show here is done by my student, Kevin Boyd. I also want to acknowledge my collaborators, Dr. John Walsh and Dr. Patrick Stowe. Also, this project was supported by the Office of Naval Research. First, what are polar lows? Polar lows are high latitude intense maritime cyclones. Different from Arctic cyclones, polar lows are mesoscale cyclones. Their diameter is typically less than 600 kilometers, and their lifetime is typically less than 2 days. They are characterized by strong surface wind. Some of the polar lows are characterized by an asymmetric structure, which is very similar to tropical cyclones. That is why they are also known as Arctic hurricanes. But some recent studies suggested moist bioclinic instability plays an important role in the development of some polar lows. As shown in this second image, you can see this polar low has a rather asymmetric structure. Polar lows associated with severe weather conditions, such as large amplitude ocean waves, heavy snow shower, limited visibility, and strong icing. These conditions can pose hazards to coastal communities and marine operations. In addition, polar lows can affect deep water formation and also oceanic circulation through strong surface heat fluxes. However, skillful prediction of polar lows beyond the synoptic timescale by global models remains a challenge because of the mesoscale structure, convective natures of these storms, and also because of the lack of observation in the Arctic and also cost model resolution. The last image shows the impacts of a polar low. These studies build upon the hypothesis that variability of polar low activity is associated with the changes in some key large-scale climate variables, which can provide predictable information on polar low activity beyond the synoptic timescale. Here, I will present 2 parts. In the first part, we will look at the development of a polar low genesis potential index that links polar low frequency with some large-scale climate variables. In the second part, we will look at the application of this polar low genesis potential index to subseasonal prediction. We assume there is a log linear relationship between polar low frequency and the climate variables, which can be represented by a Poisson model here. In this equation, on the right-hand side, xi denotes predictors, and bi is the predictor coefficient. PGI here represents polar low frequency at individual grid points. The last term I should also mention represents cosine weighting for the decrease of the grid cell area with latitude. We also assume there is a stationary relationship between polar low frequency and the climate variables across all polar low formation regions. We used the EIE5 reanalysis data and the polar low track data set. Both data sets correspond to a 2.5 by 2.5 degree grid resolution. We used the polar low genesis density function to represent the spatial distribution of polar low frequency. The figure on the right shows polar low frequency in the Arctic, in the Atlantic sector of the Arctic in the top, and the Pacific sector of the Arctic in the bottom. We focus on open oceanic grid points between 50 degree north and 85 degree north during 1979 to 2020. The Poisson regression model is fitted to long-term mean, monthly mean, polar low genesis density function and the climate variables in all calendar months over all open oceanic grid points. Here I want to emphasize we use the long-term mean, monthly mean without year-to-year variability. We used a forward selection method to choose predictors from a list of 29 potential predictors that are physically relevant to polar low formation. And this method identified two predictors. One is the static stability parameter, which is defined as a difference between skin potential temperature and 500 millibar potential temperature. The second predictor represents environmental bioclinical instability. It is defined as the magnitude of horizontal gradient of 800 millibar equivalent potential temperature. This one compares the observed polar low genesis density function on the left and our statistical fitting using the polar low genesis potential index on the right. The top two panels represent the Atlantic sector of the Arctic, and the bottom two panels represent the Pacific sector. You can see there is overall good agreement between PGF observation and the PGI statistical fitting, although the PGI index tends to smooth out some small scale features of the polar low distribution. We can also use the PGI framework to assess the contribution of individual predictors to polar low seasonality or variability. We defined the so-called fractional contribution function. You can plug in individual predictors and assess their impacts. Here we examined the impacts of the static stability parameter on the left and the baroclinicity parameter on the right. Again, the top two panels represent the Atlantic basin, and the bottom two panels represent the Pacific basin. We can see the static stability parameter makes a larger contribution than the baroclinicity parameter. It basically determines where polar lows may form, but enhanced baroclinicity can further amplify the potential of polar low genesis, especially over the Atlantic. In contrast, over the Pacific, we can see polar low formation is associated with relatively weak baroclinicity. This one shows polar low seasonality. I should have mentioned that polar lows are wintertime storms. They only occur during boreal winter. In the top two panel, the solid line shows the seasonality of the observed polar low genesis density function, and the dashed line shows the polar low genesis potential index, which is our statistical fitting. You can see there is a very good agreement between the two curves. Both show the peak of polar low activity in the winter season. In the bottom panel, we examined the contribution of individual predictors to the polar low activity seasonality. The red one represents the static stability parameter, and the blue one represents the bioclinicity predictor. You can see the seasonality is mainly determined by the static stability parameter. Now let's look at interannual variability. Again, I want to emphasize our statistical fitting is just based on long-term means, long-term mean, monthly mean data without any information about year-to-year variability. But when we use the PGI index to reproduce the year-to-year variability, we can see there is a good agreement with the observation. Here we examined different regions. The Pan-Arctic in panel A. In panel B, we have Eastern Atlantic, which is represented by the red region in the lower left map, and the Western Atlantic and the Pacific Basin. The red lines represent the observed polar low genesis density function, and the blue line is the PGI index. We can see a very good agreement in all regions. In particular, over the Eastern Atlantic, where we have active polar low occurrences, the correlation between the observation and the PGI index is 0.79 from 1979 to 2020, 42 years. Now let's look at the second part, hybrid prediction using the PGI index. In the hybrid prediction framework, we derived the predictors static stability and bioclinicity from ECMWF subseasonal and seasonal forecasts. We focus on the polar low season from November to March of the next year. The predicted polar low genesis index is evaluated against the observed polar low genesis density function derived from the polar low track data set. We used the anomaly correlation coefficient and the Hadkey scale score to assess the prediction scale. This slide shows the time series of monthly mean polar low genesis density function in red and the PGI index in blue. Again, PGI, the blue lines represent the prediction. We examine the different regions. In the top panel, we have from left to right, we have the Nordic Sea, Erminger Sea, and the Labrador Sea. In the bottom panels, from left to right, we have Gulf of Alaska, Bering Sea, and the Sea of Okhotsk. You can see we have actually a good prediction scale in terms of ACC in all regions. In particular, over the Bering Sea, the anomaly correlation between prediction and observation is close to 0.66. But on the other hand, you can see the prediction tends to underestimates the magnitude of year-to-year variability in observations. We also tried a two-tier prediction using the ECMWF S2S forecasts. Here, the 4 panels represent a monthly prediction, week 1, week 2, and week 3+4 predictions. The different color bars represent different regions. The bars here represent a Hadkey scale score. We can see in the monthly prediction, week 1 and week 2 predictions, we have positive skill scores in all regions, which indicate our prediction is more skillful than the climatology. But for weeks 3 to 4, the prediction skill basically is gone. You may ask, why don't we have good prediction skill for weeks 3 and 4? To assess the potential predictability, we tried the perfect prediction using predictors derived from the EIE5 reanalysis, which can be regarded as the truth. So this represents like the upper bound of prediction skill we can get if we have perfect information of the predictors. You can see for week there is not much change from week 2 to week 3 and 4. The fluctuations here are not statistically significant. That means the poor prediction skill in week 3 and week 4 is due to the poor prediction skill of the predictors, the static stability and the bioclinicity predictor. It's not due to the framework. If we can somehow improve the prediction skill of the predictors, we have the potential to improve week 3 to 4 prediction. We also examined the modulation of climate modes on the polar law prediction. Here I show the Arctic oscillation and the Pacific North American pattern as an example. Again, different colors represent the different regions. The top panel shows the AO, the bottom panel shows the PNA. Solid bars represent the positive phase of a climate mode, and the hatched bars represent the negative phase. Striped bars represent the neutral phase. In the top panel, you can see we have enhanced prediction skill during both the positive phase and the negative phase of AO in the Nordic Sea region. Also, in the Labrador Sea, in the positive phase of AO, we have enhanced skill. In the neutral phase, in both regions, the skill is close to 0. But what is interesting is over Gulf of Alaska, you can see the prediction skill actually is lower during either positive phase or negative phase of AO. I forgot to mention the plus and minus signs here indicate a significance. Also, in sea of Okhotsk, the prediction skill is enhanced during the negative phase of AO. I should also mention our statistical fitting actually does not include sea of Okhotsk, but the model still performs with decent skills in sea of Okhotsk. Or the bottom panel shows the impacts of Pacific and North American pattern. You can see the prediction skill over the Nordic Sea actually is lower in the positive phase of PNA. Also over Gulf of Alaska, we have a lower skill during the positive phase of PNA, but higher skill in the negative phase of PNA. Further analysis shows that the polar law variability is much stronger in the positive phase of the PNA, which is not well captured by the prediction model. Okay, here is my summary. A polar law genesis potential index is developed to represent the empirical relationship between key climate variables and the polar law genesis frequency in a Poisson regression framework. The PGI index will represent the long-term mean seasonality and the spatial distribution of polar law genesis frequency, and also the interannual variability of the observation at all scales. When we use the PGI for hybrid prediction, we can achieve skillful prediction of polar law activity over a forecast range of weeks to a month in advance. And the prediction skill varies by region and also is sensitive to some major climate modes. Okay, I will stop here and leave our publications for your reference. Thank you.
Great. So if you have any questions, we can see the discussion chat. Yeah, I have a quick question. So can you hear me?
Yeah.
So yeah, I'm a hydrologist, but I'm in a polar vortex. So we can sometimes we can get a very cold vortex or like very warm air. So any relationship between the polar vortex and also jet stream? Maybe please correct me if I'm wrong.
Oh, the polar laws we discuss here are different from polar vortex. When we talk about a polar vortex, I think you are talking you are thinking thinking of the larger scale vortex, either in the troposphere or the stratosphere, which is tied to the mid latitude jet. But the polar laws here are mesoscale vortices. They have like a very intense surface wind, which is similar to like tropical cyclones, but their spatial scale is very small. It's like 200 to 600 kilometers in diameter.
Okay, right. Thank you for correcting me. So it's more like higher latitude than the tropical, but that's
right. Yeah. Mm-hmm.
Polar lows. Okay. So any with this like extreme weather pattern, any polar lows in regularity which you found in this study?
We found, like you mentioned, the polar vortex earlier. We found actually stratosphere sun warming can have impacts on polar lows. In addition, the median junior oscillation also modulates polar low activity, which can serve as like sources of predictability on the subseasonal time scale.
Okay. So any other questions from the audience, attendees? Okay, then thank you so much. So both the Buhar and also Ju Wang from UIUC and also Columbia University. So our next meeting, we will skip December and January, and we will meet again in February 2024. It's going to be February 6th, and I will send an email announcement in the middle of the January 2024. And thank you very much for your interest for the S2S webinar, the week 3 for webinar. And I will touch base with you with the new announcement in the new year. Thank you and have a good day. Bye now.
Thank